Hello everybody, and welcome to Programming and Optimization with Intel Architecture, the hands-on workshop series. I am Andrei Vladimirov, and I will be with you for the 10 days of the workshop. Let me give you a quick overview of the general course information. This is the calendar of this September workshop. We are now in day 1, and for 10 consecutive business days, we will meet in the mornings for 2 hours. The first hour is usually a presentation, and the second hour is the hands-on part. And I will talk about the hands-on part in a second, but it's important that even if you don't want or will not be able to participate in the hands-on part by connecting to a remote server, still stick around because I will be doing demonstrations that you can follow along. We will talk about Intel parallel architecture, and then I will define the platforms that we will be focusing on: Intel Xeon processors and Intel Xeon Phi processors. And the first 2 days we will actually be talking more about Xeon Phi than about Xeon. We will talk about programming models, the native programming model and the offload programming model for Xeon Phi. But starting from day 3, we will our discussion will become very general, and we will talk about expressing parallelism with vectorization and multi-threading. And after that, we will talk about optimization. So actually 50% of the presentations are dedicated, not 50, 60% of the presentations are dedicated to performance optimization, and this is the core topic of this course. The discussions that we will have are general. They don't just apply to Xeon Phi. They don't even apply just to Xeon Phi and Xeon. They apply to any parallel processor with an architecture that has multiple cores and cached memory and vector units inside of every core. This course has a web page, and this is the URL for this web page, and let me demonstrate to you what's in there. So this page is on colfaxresearch.com, and this page is specific to the September workshop. So actually, if you are watching this as a recording, you might need to find the corresponding page, but this is where you can go to get descriptions of every session and also download the slides. The slides that I'm showing now are available, and you can just click and download, and also the code for the hands-on exercises is available on this page. Later, as the course progresses, next to this paragraph, you will see a big thumbnail that looks like a video, and it is a link to a video, and that means that all the sessions will be recorded and posted on this page. To access all the materials on this page, you will need a Colfax Research account. If you registered for the workshop, it does not create a Colfax Research account. Actually, Colfax Research is much more than just the webinars, and creating an account is absolutely free, and it takes, well, less than a minute. So go to this page to get slides, recorded sessions. If you miss any sessions, you can go back to them. Requires registration, but this is free and quick. As I mentioned, if you are watching this as a recording, you may need to look up a different page. And this page is the gateway to all the workshops. Everybody who is attending now is starting early, so you're in a good shape. But if you're watching this as a recording and want to join one of the future workshops, go to colfaxresearch.com house series, and this is where you can look up, for example, we have another run of this workshop in October, and you can actually go and watch recordings of earlier workshops from July and August. There's even more information on Colfax Research that you can use. There's video courses that we have recently posted, and one of the video courses is actually the recording of the August How series workshop, but there's another course which is a studio recorded 5-hour presentation of nearly the same material. It doesn't focus on hands-on exercises as much, but um, the structure of it is conducive to learning whenever you have a minute. We have short episodes, very concise, and pick a topic and study. If you have questions, Intel has two forms. When you download the slides, these links are actually clickable. So when you click, it goes to one of the forums. And this is where you can communicate with the community, which includes a lot of Intel engineers. You can communicate regarding the many integrated core architecture, in other words, Xeon Phi, and about general high-performance computing questions. This course is based on a book. The book is available here, xeonphi.com/book, and this is an original Colfax publication, 500 plus pages, and the book is the original source of all the topics that we are discussing, and it is the original source of all the exercises that I will be demonstrating. This is an optional, very useful, in my opinion, resource for learning in this course. So regarding remote access, this is a hands-on workshop, which means that many people will be able to connect to a remote server at Colfax, and this server has a multi-core virtualized processor and a real Xeon Phi coprocessor, and it has Intel software development tools. And you will be able to use this server to run the practical exercises that I will be demonstrating. Now, we are currently set up to provide access to 56 people who have requested remote access, and we will be adding more seats in the days to come. So even if you don't get a token today, stay tuned, and we have a wait list. We are monitoring it. If people drop out, we reassign their remote access. But even if you don't have remote access, it's still worthwhile to stay for the second hour, because I will be connecting to my server and I will be demonstrating performance optimization techniques and programming techniques live, and you will be able to follow along even if you don't have your own remote access. Regarding remote access, I will give you more instructions in 50 minutes when we get to that part. But so far, nobody has remote access. I will be sending an invitation just at the top of the hour. If you attend 6 sessions out of 10 in this workshop, and we are only able to count live broadcasts like this one, if you attend 6 sessions out of 10, you can get a certificate of accomplishment in the fundamental level endorsed by Colfax, saying that you have completed the course called Programming and Optimization for Intel Architecture. And this is the fundamental level of accomplishment, meaning that it is issued to students who attended training for courses that do not have post-training exams like this one. Visit us at colfaxresearch.com. As I mentioned, this is a lot more than just the webinars. We have case studies, tutorials, presentations, video recordings of various kinds, mostly revolving around parallel programming. A lot of our publications have downloadable code, and you can really use it to learn whether you are a beginner in parallel programming or an expert. I'm sure you will find something useful. All right, this is it with the orientation, and thank you very much for your attention. And now I'm ready to begin the presentation part. I will talk about Intel architecture and parallelism. Intel makes a lot of processors, most of which are parallel processors. They have multiple cores, but we will focus only on their enterprise-grade platforms, Intel Xeon and Intel Xeon Phi. We will not be really talking about desktop processors such as Intel Core, i3, i5, i7, or Atom, even though what we are talking about applies to other Intel platforms. But all the exercises that we will be doing will be revolving around performance optimization on Xeon and Xeon Phi. You will see that we are actually advocating portable, future-proof techniques, but this will be our treadmill of choice. Xeon is a general-purpose processor, and it is a highly parallel processor. Xeon Phi is a specialized processor, and it is also a highly parallel processor. What is the difference? What is the difference between them, and what are the similarities? The strong part of the Xeon Phi platform is the similarity with Xeon. You can take an application that's written in C, C++, or Fortran, and this application can be recompiled to run on Xeon Phi. Even more, if you have parallelism in your application and you express it with the OpenMP or MPI framework, you can expect the same frameworks to work on Xeon Phi. This is only possible because Xeon Phi is not just a computing accelerator. This is actually a processor. It is running its special Linux operating system in the card, and I will demonstrate how it works soon. It is also architecturally very similar to Xeon. It has its own memory, which does not share the memory address space with the Xeon, but the similarity is that both on Xeon and on Xeon Phi, the memory is shared across all cores, and it is cached. It has two levels of cache, level 2 and level 1. Regarding the parallelism, you have multiple cores, tens of them in Xeon, and you have multiple cores in Xeon Phi. The difference is now that Xeon has a smaller number of cores. They are clocked at a high clock speed, and they are smart. They have out-of-order execution. They have smart branch predictors. They have intelligent prefetchers. So Xeon can take workload which is bumpy and run it pretty efficiently because it has a lot of hardware to compensate for it. But this comes at a cost. All this hardware it costs money to make, and it costs power to run. So Xeon Phi takes a different approach. It has multiple cores, and they're clocked at a low clock speed. This is your power savings. But also they are not, they are very light on hardware. They are in-order cores, which makes them easier to produce. They do have branch predictors and prefetchers, but maybe not as advanced as in Xeon. And they have less cache per core, which is also potentially a power and cost-saving measure. As a consequence, Xeon Phi can either work much better than a Xeon if your code is very smooth and really targeted to parallelism and good memory access. Or if your code has a lot of serial segments, it works with memory in a poor way, then Xeon Phi actually will not be happy. So Xeon Phi is a specialized processor that can give you better performance per watt, better performance per dollar than a Xeon. But on the other hand, not every application will run well on Xeon Phi. We will focus on computing applications, and throughout this course I will demonstrate performance optimization techniques that work both for Xeon and for Xeon Phi. I want to mention two more points of similarities and differences between Xeon and Xeon Phi. In Xeon, each core supports two hyperthreads, so each core presents itself as two logical processors. And hyperthreads are a technology that allows you to mask latency. You can have two software threads running on one core, and one thread may be doing calculation and the other is doing memory access, so you mask latency of long operations in this way. This is Xeon. On Xeon Phi, on the other hand, you have 4 hardware threads per core. This is a different word. This is hardware thread, not hyperthread, and it reflects the fact that they work differently. They operate in round robin. They don't switch thread contexts at runtime. And another similarity, which has a qualitative difference between Xeon and Xeon Phi, is the vector units. Each core in Xeon has a vector unit capable of processing short vectors 256-bit wide with AVX instructions. In Xeon Phi, the vector units support longer registers, 512-bit wide, and they have a different instruction set, IMCI. So Xeon Phi is a coprocessor. It looks like this. It has a PCI Express connector, and this is how it connects to the main system. The first generation of Xeon Phi can deliver up to 1 teraflop per second in double precision. This is the theoretical peak performance, or 2 teraflops per second in single precision. It has onboard memory up to 16 gigabytes of RAM, which can deliver a practical bandwidth up to 170, 180 gigabytes per second. And this is a coprocessor which is specialized for highly parallel applications which also reach the scaling limits on Intel Xeon. Xeon Phi has been around since 2012, and a new generation is coming up soon, Generation 2. I will talk about it in a minute. To see where Xeon Phi is used, you can go to the application catalog, and you can see a lot of sectors participating. The common feature of all these sectors is that oftentimes you have code which took a lot of manpower to develop. So the continuity of programming model between Xeon and Xeon Phi is really attractive for these sectors, in that you can take code that is capable of running on Xeons. It is also immediately capable of running on Xeon Phi. Of course, the performance may not be great, but at least you can do performance optimization incrementally. And this is all that we're going to talk about in this course. As I mentioned, the second generation of Xeon Phi is just around the corner. If you were reading the news, you may have heard the code name for it, Knight's Landing Chip. It will be based on a smaller transistor manufacturing process, which means that you can put more hardware, more cores on the same chip, and they will be more power efficient. In fact, the official numbers show performance improvements around 3x compared to the first generation. But a very attractive feature that the second generation has is that you can get the second generation of Xeon Phi either as a coprocessor, a card with a PCI Express connector, or as a socket version, meaning a processor. So the second generation of Xeon Phi can be the CPU, and you boot the operating system on it, and it still has the in-package high bandwidth memory, but it can talk to the main memory on the board directly, not across a PCI Express bus, but directly, which is much higher bandwidth. To learn more about the second generation of Xeon Phi, you can watch this webinar, and this link is clickable once you download the slides. I think a picture is worth 1,000 words, so I've prepared to show you this demo. This is a demo that we ran at Supercomputing 2012, and this demonstrates a very simple direct n-body simulation. So I have a number of particles. Each particle interacts gravitationally with every other particle, and I calculate how these particles move in response to gravitational forces. So this is calculation running on a dual socket Xeon, and now the same performance critical code runs on Xeon Phi. This is not as optimized as it could be, but the key point here is that we are using the same code on the CPU and on Xeon Phi for a really attractive performance improvement. And actually it is easy to scale across more than one Xeon Phi coprocessor in the system, and it runs yet slightly faster. Once again, the reason I'm showing this is not to impress you with specific numbers of how many flops per second we achieved, but rather to demonstrate that the same code can run efficiently on Xeon and Xeon Phi, and this is a paper that discusses this workload. You can get it from Colfax Research. It is very important to realize that even though you have huge performance potential in Xeon and in Xeon Phi, it takes effort to unlock this potential in your software. And To illustrate what's inside of Xeon Phi, I'm showing this die organization diagram. This is more than just for amusement. Um, I will point out the aspects of this architecture that are important to programmers. So this is a Xeon Phi processor chip, and it is built around a ring. It's called core ring interconnect, and this is a high-speed data bus. Around this ring, I have multiple cores. Each core has its own slice of the level 2 cache, and I also have a distributed tag directory which maps memory addresses to caches. Also around this ring are sprinkled 8 memory controllers that connect you to the onboard RAM. This RAM has the GDDR5 technology, high bandwidth RAM, and there is one S box. This is the PCI Express Gen 2 controller. This is the controller that connects Xeon Phi to the main host system. The reason I'm showing this is to illustrate that cores have different distance to different parts of the cache. So when this core is talking to data in its local cache, this is fast. But when it's talking to data in a remote cache, it first has to go ask the tag directory, do you have this? Who has this memory address? This tag directory replies, well, core number 30 has this address. Okay, then this core goes, core number 30, give me this cache line. And then this traffic goes across the ring. This is a reminder to the programmer that Xeon Phi is very sensitive to data locality. If you organize temporal and spatial locality of memory accesses in Xeon Phi in a favorable way, and cores always talk to their local memory, you get potential performance boosts. Another diagram that I wanted to show, once again, is not for amusement, but as a reminder to programmers on the importance of optimization. This is one of the cores. So Xeon Phi has up to 61 active cores, and this is one of them. It is connected to this interprocessor network, core ring interconnect. It has its own slice of the level 2 cache, and the level 2 cache is, well, the slice is private to each core, but the aggregate of all the level 2 caches is kept coherent by hardware. And the level 2 cache is cached by the level 1 cache, and there's two arithmetics unit. One is the scalar unit, and the other is the vector unit. This picture shows them about the same size. But in reality, the scalar unit is only around 2% of the core surface area. The performance is in the vector unit. This is where you want to do the math. What it means to do the math with vectors, I will explain later, and we will have dedicated exercises on vectorization and optimization of vectorization. But the reminder here is that if your application ends up running in the scalar unit, if it is not capable of using vectorization, then you're just using a tiny fraction of the capacity of the chip. So vectorization is very important for Xeon Phi. Things you can do with vectors, this is a brief list, and I will focus on this later, so I will not read this list out loud, but you can do arithmetic such as add, multiply, subtract, divide. You can do transcendental functions, comparisons in vectors. You can do type conversions, and also you can use vectors for bitwise instructions. Now is a performance chart. This is a cartoon. This is not a measurement. It is showing the theoretical peak performance in units of gigaflops per second, billions of floating point operations per second, on two platforms. Green is a dual socket high-end Intel Xeon processor, and blue is a high-end first generation Intel Xeon Phi coprocessor. This first set of bars shows the ideal case when I have parallelism that allows my application to use all the 61 cores and all of the vector units. I can get up to 1200 gigaflops per second in double precision on Xeon Phi and around half a teraflop per second on the Xeon. Now, what if my application is not capable of using vectorization? It runs in the scalar unit. There is a penalty for that on Xeon. a factor of 4, but the penalty for that on Xeon Phi is a factor of 8. So now Xeon is just barely ahead of the Xeon Phi. I'm sorry, Xeon Phi is just barely ahead of the Xeon. Now this case is not really realistic. If your application is doing this, you probably wouldn't run it on Xeon Phi. But still, this is one core performance, which uses vectors. So Xeon Phi is marginally behind the Xeon. And this is one core that is not capable of using vectorization. So no vectorization, no multithreading, no parallelism at all. Then Xeon Phi will be completely miserable. Which shows that Xeon is a parallel processor. It likes data parallelism and thread parallelism, task parallelism. But it is more versatile, meaning if you don't have this parallelism, it can deliver better performance than a Xeon Phi. Xeon Phi also likes parallelism, but without parallelism, it is completely useless. Now here's another performance plot, which is a reminder of another prerequisite for good performance on Xeon Phi. Now this is not a cartoon, this is actually a measurement, and this is a measurement of the memory bandwidth. And the memory bandwidth is measured again on Xeon and on Xeon Phi in units of gigabytes per second. So this is how fast I can transfer data from the system memory to the CPU, or from the onboard Xeon Phi memory to the Xeon Phi cores. So there is no PCI Express transport here. This is just the memory of the system streaming data into cores. For measurement, I used the industry standard stream benchmark in the triad mode. What it does is it takes one long array and it throws all cores at this array. And these cores read this array, multiply it by a number added to another array, and write it back to memory. So there's 3 operations on 3 arrays. That's why it's called the triad. So Xeon Phi is about twice as fast as Xeon in this test. But then I changed my memory access pattern. Here, the memory access pattern was very predictable, streaming. I was going sequentially in memory. But now I added some randomness to the memory access pattern. That's how I did it. I allow the core to read a 4 kilobyte block, and then it has to jump in memory to another location, which is random. The penalty for doing that on Xeon is almost a factor of 2, on Xeon Phi almost a factor of 3. And then I increase randomness even more. Each thread runs the triad test on 1 kilobyte block, and then it jumps in memory to another location. There is further some penalty on Xeon, but even greater penalty on Xeon Phi. Once again, this is a reminder to the programmer that a prerequisite for good performance on Xeon Phi is good memory access pattern. Good means that the memory access pattern should be sequential, ideally, or another case is when the memory access is actually insignificant, meaning that the runtime is dominated by arithmetics. And this is when you get performance like that. This is what I showed in the previous slide. So let me go further and show how this translates to real application performance. As I showed, not using memory efficiently and not using vectorization and multithreading efficiently can give you a huge performance penalty. And this is what it looks like in a real application. This is a case study that we did with Stanford University on a library called HeatCode. It stands for Heterogeneous Library for Transient Cosmic Dust Emission. So this is an astrophysical application. There's a paper describing it. It is pretty complex. It computes the emissivity of cosmic dust grains illuminated by stellar light. And it has some dense linear algebra. It has some bandwidth bound operations. It has a little bit of latency bound operations with stochastic memory access pattern. It uses a lot of physics data, so it was difficult enough to develop so that it works correctly. But the project that we were targeting this application for, with the existing code that we started with in 2012, would have taken 6 years. So this is the original performance on the Xeon processor using all cores. We thought, well, maybe on Xeon Phi it will be a little bit faster, and we recompiled this code and ran it on Xeon Phi. and this was our performance. Now, notice that this is a log of performance. So the performance on Xeon Phi was an order of magnitude worse than on the CPU when we started. And then a story happened that everybody who worked with Xeon Phi keeps telling. The story is that you start optimizing on Xeon Phi. Some optimizations may be algorithmic, meaning that we chose a better algorithm for working with the problem, and that gave us a huge boost. But then other optimizations were actually making the code more efficient. So we are making the algorithm closer to hardware. We adapted so that it can use all threads that are available, so that the memory access pattern is favorable, so that we are doing meaningful things inside of every vector lane, optimizing memory access pattern, optimizing optimization, optimizing offload traffic, and as we do that, performance on Xeon Phi keeps growing. Actually, the difference is really huge between this and that. Well, actually, let's compare the difference between this optimized performance on Xeon Phi and unoptimized performance on Xeon, the baseline. I would be tempted to say that we got something like a 200x speed up. But that would be unfair because I'm comparing optimized code on Xeon Phi to unoptimized code on Xeon. Now here's the best part of the story. Because of the programming model continuity between Xeon and Xeon Phi, I can take this optimized code and run it on Xeon. And when I did that, what we found is as we optimized for Xeon Phi, the performance on Xeon also kept creeping up. And eventually, the performance optimization, the performance boost from just optimization on Xeon was a factor of 100. Finally, Xeon Phi works twice as fast as Xeon, so 2x acceleration doesn't sound really mind-blowing, but this is a good speed-up factor considering that this Xeon Phi consumes the same power as the Xeon, and that actually costs less than the platform with the Xeon, so 2x with the same code is not a bad deal. But the very important part is this huge gap of 2 orders of magnitude between unoptimized code and optimized code. You can refer to this paper for more details on what exactly we did, but we will see the details later in the course. So Xeon Phi at this point I hope sounds like an attractive platform, and I want to talk a little bit about what it means to have a Xeon Phi in the system. The first generation of Xeon Phi coprocessors is, well, a coprocessor, meaning that you have to have a host system like a workstation or a server, and then you can plug Xeon Phi cards into it. So here we have 2 Xeon Phi cards with active cooling solutions. They have a fan on board. There we have 8 Xeon Phi coprocessors in this 4U server with passive cooling solutions, so air goes straight through them. These are just some of the examples of the systems that Colfax makes. The reason I'm showing them is to illustrate that you can both use it in a workstation and in a data center. To be able to utilize Xeon Phi, you have to have what's called MPSS, the Intel Many Core Platform Software Stack. This is a software stack that contains drivers for Xeon Phi. It contains tools for working with Xeon Phi configuration, and it contains the operating system which runs on Xeon Phi. MPSS is free to obtain. This is a clickable link in the slides where you can get MPSS. And this MPSS will allow you to run applications compiled for Xeon Phi. Besides MPSS, if you want to develop applications for Xeon Phi, you will need a compiler capable of producing code for it. To the best of my knowledge, the only compiler that does it for the first generation of Xeon Phi is the Intel compiler, and Intel makes C, C++, and Fortran compilers with support for the Xeon Phi architecture. Notice that if you get if you get the latest and greatest compiler, which is the 2016 version, there is one compiler that works both for processors and for coprocessors. So you don't have to get a special compiler for Xeon Phi, but you have to get a modern one from Intel to use it. The compiler you can get independently or as a part of a bundle such as Intel Parallel Studio XE, which also comes with performance optimization tools, mathematics support libraries, and some clustering tools. In this course, the very last session will actually demonstrate using two of these tools, the profiler Intel Xeon amplifier and the math library MKL. But most of this course is focused on using the compiler. We are using Linux in our systems, and when you use remote access, you will be in a Linux environment. So this is a Linux console listing that demonstrates the interaction between the host system and Xeon Phi. We will do it live, but let me just explain here what's happening. My username is Viga. I am sitting on host called Lyra, which is actually a workstation. No, this is a server that we have for testing. I query the devices on the PCI Express bus, and two of them show themselves as Intel Corporation Xeon Phi coprocessor 7120. This is the model number. Then I query the service called MPSS, and it is running, which means that the driver is loaded, so I can talk to Xeon Phi. Well, okay, this is just some device on my PCI Express bus. What's special about it? This is where the special part starts. I query my hosts file. The meaning of the host file is it contains IP addresses and host names of the hosts that are extremely important to the system. And it has two interesting entries, Lyra Mic 0 and Lyra Mic 1. These are actually host names of my Xeon Phi coprocessors. They are configured by default by MPSS configuration tool, and they have IP addresses. So I can ping these IP addresses. And even more, I can type SSH Mic 0 and I will log into the Xeon Phi sitting behind this host name with this IP address. So when I get logged in, you see the prompt changes from Lyra, it changes to Mic 0. And now I am inside of the operating system which runs on Xeon Phi. So Xeon Phi acts like a computer inside of a computer. It has its own operating system. It is a Linux. It has a kernel. It has all the normal, it has a file system. It has all the normal components of it, like home with user accounts, etc with configuration files, bin with executables, and so on. It also has proc, where I can query my CPU information. And what I see is that my CPU identifies itself as a processor with 244 logical processors. What is 244? Xeon Phi has 61 cores. Each core has 4 hardware threads. So 61 times 4 is 244. As I mentioned, Xeon Phi has a file system, and the files in this file system actually live in a RAM disk, which is configured out of the box. This RAM disk takes up some part of the operating system of operating memory on Xeon Phi, but the way it works is I have my host. It has hard drives, it has network interconnects, and the host has a PCI Express bus into which I plugged in my Xeon Phi. When my application runs on Xeon Phi, it can read and write files stored inside of Xeon Phi on the RAM disk. This is a volatile storage, so I reboot the system, files are gone. There is another way to work with files from Xeon Phi. If you want to store them on a non-volatile system, you can dedicate a hard drive on the host, or a partition on this hard drive, or a file that works as an image file on the host, and you can give control to Xeon Phi to this file. The way it will look is on Xeon Phi you will have a mount point. When you write files or read files from this mount point, actually the traffic goes across the PCI Express bus, and the files, the data, end up on the host on the hard drive, but it looks like you're just working with some directory on Xeon Phi, so transparent. You can also use network storage on Xeon Phi, and specifically it supports NFS, network file sharing. This is a standard Linux distributed storage, which is really easy to configure. It can also work with Lustre, which is a high-performance, scalable storage, quite a bit more difficult to set up, but it is scalable and it can operate across InfiniBand interconnects, achieving very high throughput rates. And once again, the way you work with files is your application will read and write files in some directory on Xeon Phi, and the traffic will transparently go to the storage server. The way that Xeon Phi can communicate with external servers is actually also very important. And I'm showing this is information mainly for system administrators, but it is also important to application developers because, well, on the one hand, if you have a workstation, then you are on your own with configuring networking. On the other hand, if you have a data center, a computing center, you may need to work with your system administrators to configure the right things for you. So by default, the CPU has a Xeon Phi coprocessor, and the CPU is the host. It has a network interconnect, such as a 1 gigabit Ethernet. By default, Xeon Phi does not see this network interconnect. By default, Xeon Phi can only communicate within the system. But you can tweak the configuration as described in this paper so that Xeon Phi joins the network of the host. So Xeon Phi will think that it has a network interconnect, and it can claim an IP address on the private network of the host. So Xeon Phi can talk to other coprocessors across the network. And this traffic is routed across the host system, and there is a limitation on the performance of this traffic. Actually, you won't even get Ethernet bandwidth working like that from Xeon Phi, but this is easy to set up and it is useful for administrative tasks. There is another way to transfer data out of Xeon Phi to other coprocessors in the cluster, and this is the CCL technology, coprocessor communication link. In this mode, Xeon Phi can talk directly across the PCI Express bus, bypassing the host to an InfiniBand interconnect. InfiniBand is a technology for high-speed, low-latency network interconnects. If you have such an interconnect in the system, Xeon Phi can use it directly, and you can get to much greater data throughput rates, again as described in this system. So Xeon Phi actually can work as an independent compute node on your network. Because you have this capability to communicate between individual Xeon Phis without the involvement of the host, and because Xeon Phi runs its own operating system, there are two models for using Xeon Phi in the system, which I will review now. The two programming models are called the offload model and the native programming model. The offload model may sound familiar to people who have used GPUs, computing accelerators. In this model, you write your application so that it starts on the host CPU, and most of the operations, whatever operations you need to initialize data, work with files, will run on the host. Then at some point in your code, you will have a statement, a directive, such as this one, pragma offload target make. And this directive tells the compiler that at this point, you want to communicate to the Xeon Phi driver, and you want to take a piece of code inside the scope of this pragma and push this code to the coprocessor across the PCI Express bus, run it there, and then return the results. There is another way to program Xeon Phi, and this is the native programming model. In this model, the host is not involved. The host is only needed to boot the system and boot the Xeon Phi, but at runtime, it does not participate in calculations because the entire application can run on Xeon Phi. Xeon Phi is a coprocessor, so it has to have the host for functioning, but to run applications, Xeon Phi doesn't need the host. It has its own Linux file system. It has its own networking capabilities, so you can run the entire application from the coprocessor. The performance is a different question. If you have coprocessor communication link set up, then probably communication efficiency will not be a great concern, well, at least just marginally greater concern than on the host. If you're working with files, then again, if you have Lustre configured, then you work with files transparently with high performance. But it means that you don't have to insert any directives in your code. The code that can work on the host can be recompiled and run on the coprocessor without any code surgery. This is the programming model that I will talk about today. Tomorrow, we will talk about the offload programming model. Because you have these two programming models, and you have Xeon and Xeon Phi coexisting in one system, in principle, uh, you have many approaches to programming your applications. For example, if your application has a lot of serial parts, it doesn't parallelize well, or it has a lot of file I/O operations, then you can run the entire application on the Xeon, on the host. But sometimes parts of your application are serial and they need a versatile processor such as Xeon, but other parts are highly parallel, and you want to offload the highly parallel parts to the Xeon Phi. This is where you can use the offload model. Sometimes your entire application is highly parallel and you want to use both Xeon and Xeon Phi. You can run it in symmetric mode. So parts, you will scale the problem. Xeon will be responsible for one part of the computation. Xeon Phi will be responsible for another part of the computation. The computations will be of the same kind. They will use the same code, but probably work on different data sets. This is the symmetric mode. And finally, you saw a server that has 8 Xeon Phi coprocessors and 1 CPU. So in this case, symmetric will actually be a drag because you will have to load balance between Xeon and Xeon Phi. If you have really high compute density in Xeon Phi, you can run many core hosted applications, meaning that you only use Xeon Phi and you forget that you have the CPU. Here's when the code starts. I will demonstrate a hello world application for Xeon Phi in the native programming model. And we will later go to the hands-on part and we will run this application live. This is the minimal hello world application for Xeon Phi. It is written in C, well, I treat it as C++. It says, hello world, I have so many logical cores, logical processors. And the number of logical processors is queried using a Linux system call. So when I compile this application, I will use the Intel compiler. ICPC stands for Intel C++ compiler. When I compile just like that, giving it the source file, it produces an executable called a.out. I run this application on the host. It says, hello world, I have 48 logical processors. Well, I have an Intel E5-2697 V2 processor. It has 2 sockets. Each socket has 12 cores, and each core has 2 logical processors, 2 hyperthreads. So I have 12 times 2 times 2, 48. This is the CPU, the Xeon. How do I run this application on Xeon Phi? I cannot use the same executable because Xeon Phi is not binary compatible with the Xeon. But I can recompile the same code with the argument -mmic. This is the argument that tells the Intel compiler that you want to cross-compile for the Xeon Phi architecture. But Xeon Phi is a standalone compute node for all intents and purposes. So I have to get my code to that compute node somehow. I will use SCP, secure copy, to copy my executable file to Xeon Phi. This is the command. And then I can log into the Xeon Phi coprocessor. Now I'm inside of mic 0. I'm inside of my user home folder. And when I list my home folder, I find a.out. This is the executable. And then on Xeon Phi, I run a.out and it says, hello world. I have 244 logical processors. You cannot go to Xeon Phi and compile your application there. You have to compile on the host, and then you have to transfer the executable to Xeon Phi. Sometimes you can use SCP for that, but other times you may configure your system so that your home directory on Xeon Phi is actually NFS shared with the host, and then actually you don't have to do that. Now this SSH into Xeon Phi and run is, well, basically the workstation scenario. If I have a cluster, I will be able to use a different framework called MPI, which will do all this staging of executables for me. But the bottom line, I recompiled the code with -mmic, I did some magic to get the code to Xeon Phi, and finally it sees all the 204 logical processors in the Xeon Phi card. There is a convenience tool if you want to just quickly benchmark something. It's called Mic Native Load X. We will experiment with it. This tool you can use from the host. You give it the executable for Xeon Phi, compiled with -mmic, and this tool copies this executable to Xeon Phi for you. It also picks up all the libraries that are specified in this library, in this environment variable, sync.d library path. So if my application wants libraries from one of these directories, Mic Native Load X will pick them up, transfer to Xeon Phi, and then it will be able to run my executable there. It is not for performance critical applications, but this is a convenience feature. You don't have to do the SCP SSH. One very important difference with the previous route is that Mic Native Load X is more like an offload application. It doesn't run under your user, it runs under a special user called mic user, and the consequence is that you may have issues with file permissions, so yeah, this is not for production runs, in my opinion. So the native programming model doesn't take very long to learn. All we had to learn is the -mmic compiler argument. And I showed a very primitive example, hello world application, that I was able to compile for the Xeon Phi architecture. One file, very short, no issues. In fact, the same procedure works for more complex applications. And that includes many applications out there that are open source and, for example, use auto tools for compilation. This is an example. Here I take an application called GMP. This is the GNU Multiple Precision Library. And I pull the tarball of this library directly from the internet. I untar it, extract the library. And then usually to compile this library, I would run two commands, configure and make, because this library comes with auto tools configuration. Suppose that I want to compile this library for the Xeon Phi architecture so that I can use applications that rely on GMP on Xeon Phi in the native mode. I will have to compile my application with the Intel C compiler. This is why I have CC equals ICC. So CC stands for C compiler, ICC is the Intel C++ C compiler. And to cross-compile for Xeon Phi, I will have to use the argument the argument MMIC. To pass this argument to configure, I use C flags. Usually, when I do that and I run configure, it will make a few configuration steps and then it will bail out. It will say, oops, I just produced an executable, but this executable doesn't run. So your compiler is broken, your system is broken, I don't care, I don't want to compile. This is why I have this cheat flag, host equals x8664. It just tells the configure script that I am cross-compiling, so it doesn't have to check that executables run. These flags 1, 2, 3 are sufficient to compile a lot of open source applications. Sometimes you run into problems, and this might happen when you have either dependencies of this library, then you first have to compile the dependencies, or when you have code that just won't compile for Xeon Phi. For example, assembly. Xeon Phi has its own set of instructions, so if you use inline assembly in your code, it may not compile for Xeon Phi if it just doesn't have these instructions. If you use assembly in your applications, you are risking to make your code non-portable, meaning it will compile for Xeon but not for Xeon Phi, or it will compile for Xeon Phi of the first generation but not the second generation. And then it's up to you as the programmer whether you want to provide a fallback route. Well, GMP actually did provide a fallback route. I can specify disable assembly, and then GMP pre-processes out all the assembly from the code. It uses high-level language, and then the code compiles. But of course, the performance is questionable in this case, but our goal here was not to get performance, but just to cross-compile the application so that I can start running my applications on Xeon Phi. As I mentioned, there is a framework called MPI that allows me to scale my application across multiple compute nodes. This application, I'm sorry, this framework um, is familiar to many people in HPC. I will not really focus on this framework a lot, but if you are familiar with it, you can recognize a basic Hello World application. In this framework, each process will run this code, but I will run different processes on different machines, different compute nodes, or different Xeon Phi coprocessors. And they will be able to find each other by calling MPI init, and they will be able to determine their role in the process um, by querying the rank. The rank is just the number. Um, 0, 1, 2, 3. And this rank can be compared to the number of processes in the MPI world, and then you can determine what you have to do as process number 1, 2, 3. When I use MPI with Xeon Phi coprocessors, I have to use the MPI wrapper around the Intel C++ compiler with the argument -mmic to produce a special executable. And then, well, I might need to stage my executable to Xeon Phi. But then I can set a special variable impi mic equals 0, which will tell the MPI library that I'm going to run it on the Xeon Phi architecture. The result will be that the application will run, and I specified that I want to run on this host using 2 processes, so I've just run my first parallel application. It used 2 processes on Xeon Phi. This is a very important listing because it demonstrates that you can use the same code that you would use for clustering on Xeon. You can use the same code on Xeon Phi. You just have to cross-compile, and you have to run with a special argument impi mic equals 1. Of course, if you have a cluster, you may want to run on multiple compute nodes, and you can do it like that by specifying different hosts in the command line. Or you can specify the list of hosts on which you want to run in the hosts file, hosts.txt. And this is the list of hosts with the number of processes that I want to run on each host. I will probably have to use a trick like that to allow MPI to distinguish between the Xeon executable and the Xeon Phi executable, but then the command to start my parallel application on a cluster is very compact. Just MPI run, machine file, and then the executable name. And here I'm running on one CPU, on one Xeon Phi coprocessor, and on another Xeon Phi coprocessor. These are all in the same machine, but potentially, if networking is configured correctly, I could run everything across multiple compute nodes. I've discussed the native programming model for Xeon Phi coprocessors, which sounds really easy. You just take the code that was already written for the CPU, compile it with -mmic. I will demonstrate this in the hands-on part, but before we go there, I want to give you, I think, 1 or 2 slides with a brief overview of what we will discuss today. So in contrast with the native programming model, there is the explicit offload model. When you start your application running on the host, but then you have special directives like pragma offload target mic, and everything inside of the scope of this directive can be run on Xeon Phi. When you use the the offload programming model, you don't have to use -mmic, and you start your application from the host, and it can run both on the host and on the local coprocessor. I will discuss the details of the programming model tomorrow, so I will not pause on these slides. I'm just showing them as a preview of what's coming tomorrow. But it is important to realize that in clusters, these 2 programming models give you access to 2 clustering options. One option, you have one compute node, another compute node with Xeon Phi coprocessors inside. One option is you can put MPI processes only on the hosts, and then you can use special statements in your code to offload parts of the application to Xeon Phi coprocessors local to this compute node. In this case, you have to modify your code, but you have fewer MPI processes. Another option for clustering is you can put MPI processes directly on Xeon Phi coprocessors. In this case, you don't have to modify the code, well, unless you have to implement load balancing between CPU and Xeon Phi. But just to run, you don't have to modify the code, and it will scale across the cluster. There is a paper that demonstrates doing just that for a Monte Carlo code computing Asian option pricing. And I will not play this video, but when you view the slides later, I recommend viewing this 2-minute video. It's self-explanatory and it will be a guide to this paper. We call it heterogeneous clustering with homogeneous code, meaning that we can use CPUs and coprocessors using the same code base. So we talked about Intel parallel platforms, and we focus on Xeon and Xeon Phi. They are both parallel processors. The difference is that Xeon is versatile. It is a general purpose processor. Xeon Phi is specialized. It will only work well with code that has a lot of parallelism and good memory access patterns. And in this case, it can deliver better performance than Xeon. And that applies to better performance per system, better performance per watt, per dollar. But it is not for every application. We will learn how to design applications so that they run both on Xeon and on Xeon Phi and on future generations. But as of today, we are working with a coprocessor form factor, so we have to use one of the two programming models, native or offload. In the second part of this presentation, in the second hour, I will move on to the hands-on part. And tomorrow we will discuss offload. And as a reminder, starting from day 3, our discussion will become completely generic. We will be talking just about parallel programming and optimization. We will not be focusing on Xeon Phi, even though Xeon Phi will be our litmus test for everything that we are doing. This is the end of the presentation part. And we will now do a 2-minute break. During this break, you can do what you want, but I will make sure that the people who attended today will have remote access. And then we will go and set up remote access to our systems and start the hands-on part. So let's reassemble in 2 minutes, maybe 3 minutes. See you soon. Stay tuned. right, welcome back, and let's shift gears at this point and do a couple of things. So first of all, I want to point out a feature that you have in your webinar interface. There is a little box that says questions, and some people have been using it, so thank you very much. Um, Usually, we run these webinars as a two-man operation where my colleague responds to all questions live. This time, this is a one-man operation, so I, I don't always see your questions immediately, but I really do encourage you to type. I will usually answer with voice, and if there's a little bit of lag, I apologize for that. But thank you for participation. That said, feel free to use it. Feel free to use the questions functionality, but don't blame me too much if I don't respond immediately. Another announcement is the hands-on part. So what I just did is hopefully everything worked, and I send invitations to people who are present and to people who requested remote access when registered. So you should be able to go to your mailbox and receive an email that looks somewhat like that. The subject is remote access to Colfax training developer training server. It comes from Colfax Research, and it says, dear such and such, we've provided you access. It really urges you to connect in the next 24 hours. Why is this important? We really like people to connect to our systems, and we really like them to use it. But sometimes we send an invitation and the person changed their mind about using it or is unable to accommodate it in the schedule, or maybe having technical issues and we don't know, and we see that the seat is unoccupied when other people are waiting for it. So we really ask you to act in the next 24 hours to connect once, and then we know that you're active, you've gone through all the issues, and you resolved any issues, and then that you are going to use it. If you have any issues, just respond to this message and we will help you. But the instructions are basically here. Go to this page and enter this token. So I will copy this token, go to this page and enter it. I will now demonstrate the procedures for setting up connection. Don't worry if you are not able to follow along with me. You can always go back to this page and review all the connection instructions. Also, this video will be posted. It will be posted online on this page. Let me demonstrate. colfaxresearch.com/how1509. The video will be here, so you will be able to review the connection instructions. So if you're not able to follow along with me, don't worry. Just stay tuned, watch the demonstration, and then you can set it up later. So first, I will demonstrate the procedure for people using Windows, connecting from Windows. This is a little bit tricky, so it will take a while. If you're using Linux, you can mute the sound, just click here, or if you're on a Mac, this is really easy to follow. I'm sure you can set this up really quickly. Windows is a little more tricky. So from Windows, first, I need to click here and then download the access key. I click. It suggests to save this file. I will actually choose save, and I will save it. It goes to downloads. Or if you're using a different browser, there will be a question. Now I need a tool called Pagent or Pagent. I don't know how to read the name of the tool, but you can download this tool here and scroll down. So you can just download the file, save it, and then I think you can just run it. Did it run? So when you run it, it looks like nothing has happened. But in fact, something did happen. Pagent ran, and now it's sitting in your taskbar. This tool allows you to handle access keys, and now I have to load this key into this tool. So let me show you how it works. I will be doing a little bit of magic with my system. How do I do this? Yes, so hang on, I'm changing the display. Yes, so now you should be seeing my other display, and in this display I have the taskbar. So what you should look for is in the taskbar here, or actually under the triangle, there is this little icon that looks like a computer with a hat. So I have to right click and choose Add Key, and then navigate to wherever I downloaded the key, usually in Downloads. Here it is, open. Now, it looks like nothing happened, but it worked. So if I go back to Pagent, right click, View Keys, this key was added. So done. If you reboot your computer, you will have to set up Pagent again, but for now, we don't have to. So now allow me to switch back to my other display. And in this display also, let me see if there's questions. I see some questions coming in. I will address them when I'm done with the remote access. So we've set up the key. Now I need to download and run another tool called PuTTY. It actually comes from the same page, and this is the tool that allows me to set up secure outbound connections to SSH servers, such as the server that we're running now. I can just click here, save, and I would rather save it somewhere where I can find it, like on my desktop, but for now, here is fine. So I have to run PuTTY, and PuTTY actually opens a window that looks like this. Here's what I need to do in this window. This part is a little bit tricky, but bear with me. So hostname, I have to type training colfaxintl.com, and this is again all in the instructions. I keep port as 22. Then I go here under connection data and type username student. So once again, the session was training.colfax-intl.com, connection data student. And now the tricky part, I have to go here. I clicked SSH, and then I go to tunnels. And I have to do something here which is explained in the instructions. So let me put it side by side. And there, open PuTTY and configure the first session. Training Colfax did that, and now the tricky part. So source port, I have to type 4022, and destination, it is different for different people. For me, it is localhost colon 5092, but for you, the number may be different. I do that, and then I have to click add. So it has to appear here. This was a lot of work, so I don't want to have to do it the second time. So I go back to session, and I will save it. I will call it cdt jump host or whatever I want, and click save. Now, the moment of truth, I click to see if it worked. I just need to click open, and then it opens a window that looks like this. Sending username, authenticating, warning, SSH, open SSH 53. This is what I want to see. So I stop here. What this session does is it opens for you a tunnel to your own training server on our network. So I will have to keep it running. While it's running, I have a special channel that allows me to go to my training server. And I will actually have to start another session of PuTTY. So I will keep this running, move this away, and go to PuTTY once again. So I ran PuTTY, and now I have to set up the second PuTTY session. And the instructions explain how. Hostname will be localhost. So I will be connecting to localhost port 4022. This is my special channel. And I will go to connection data, username student. And because I don't want to do this again, I will go back to session, type cdt my host, and click save, and then open. So there we go. I have two windows running. One window opens a tunnel for me. The other window logs me in. So now I am inside of the Colfax system, and this is the Linux terminal. If you are comfortable using the Linux terminal, that's all you need. In fact, if you want to open two terminals, you can go here, start another version of PuTTY, and now I don't have to do any work, just double click my host, and it opens another window. So now I have one window for editing files, this window, and one window for running applications, that window. That's great. Now, many people are not familiar with Linux terminals. They would prefer remote graphical desktop, and there is a solution for you too. The way to do it is to first set up a password. You will have to use a password, and the command to set up a password is well, first let me unlock these instructions. Remote desktop. I will set up a password, and the command is sudo password student, and I will set it to anything I want, and I will not tell you, and don't tell anyone what you set it to. But now I can close this. So to start remote desktop, you will have to install one more application. This application is a remote desktop client, no machine. I do not recommend that you do it now, because if you do it now, it will install and then it will ask you to reboot your Windows system. I've already done that, so I will demonstrate what you will do afterwards, but it is really easy to follow. So I will run no machine, which is already installed. So for now, just use the terminal, or if you cannot use the terminal, stay put, and then an hour later you will set this up. So here I will click create new session, and I will choose protocol SSH, next screen, host, localhost, port 4022. This is all in the instructions. Continue. Use the no machine login. Don't change anything here. Don't change anything on this screen. And I will call it connection to my Colfax training server. Now I have a new icon like this, and if I click and then it's complaining to me, now I'm intentionally demonstrating a problem. Could not connect to the server, connection refused. It means that you have to start this first PuTTY session. So go back to PuTTY and open the tunnel. So this jump host is very important. You have to keep this connection running. This opens access for you. Now I have access. I go back to no machine, double click, and now it allows me to log in. So I will log in as student with the password that I have just sent. I can store it if I want, don't have to. And when I click OK, it will give me one prompt. This will only be one time. I will click here to save, and I will choose genome. Always choose genome for this, and then you will not be asked again. And then I will have a lot of other screens and prompts which are somewhat annoying, but they can be informative. Oh, no more prompts. I guess I'm lucky, but you will go through prompts that just demonstrate to you how to use this tool. So this is the graphical remote desktop on a Linux system that has a Xeon Phi coprocessor. This is my training playground. Let me expand this to the full screen. Excuse me. Yes. Expand this to the full screen, and you will see that it's frozen. Not so good. So what you have to do is this one-time procedure. Mouse over the top right corner. Click. Go to display. Choose resize remote screen and click done. and done again. And now when I maximize, it resizes the remote screen, so hopefully you can see everything. So at this point, I hope I've shown enough for you to be able to follow along when you connect from home. But let me start working here. So I will go back to No Machine. This is where I'm going to work. I've demonstrated connection instructions for Windows users. And I will not demonstrate connection instructions for Linux and Mac users because this is relatively easy. If you have any issues, email us at that return email address. So now let me address the questions. One question is, I did not receive an invitation email for remote access. So this means one of the two things. Either when you registered, maybe you did not request remote access, but if you did, maybe you tuned into the webinar a little late, because I've only sent out remote access invitations to people who are connected now. So if you did not receive it, it's either one of these two things, or maybe a human error. So the person who asked that they did not receive an invitation, I got your name down. I will double check, and then I will send you an invitation once I disconnect. And if you expected an invitation but did not receive it, then write to us at training@colfaxinternational.com. Let me show you the email address. Yeah, if another question like that came in, so I will mark everybody who asked, or you can write to me here, training@colfaxinternational.com, and after I disconnect, I will make sure that everybody gets remote access, because we still have free seats. So stay tuned, and sorry for the inconvenience, but I think this will be time well spent, and your invitation is coming soon. So I'm going back to No Machine, and I will be working mainly with I'm sorry, a lot of clicking. I think it will be, yeah, that's good enough. So I will be working mainly in the terminal, and if you're connected with PuTTY, you can do all the same things as I'm doing. Let me make it a little bigger so you can see. Okay, so I'm logged in. I am student at CDT, and when I list, there is a file called labs.zip and labs. This is where we'll be working. If you decided not to connect to a remote training server, but instead you're using your own server, you can get the exercises from our site, the same location as the slides. So hold on. There we go. So this is the URL of the page, colfaxresearch.com/how1509. If you can't reproduce this, go to colfaxresearch.com. Oh, sorry. Go to colfaxresearch.com, go to training, web-based. And this will show you all of the events. So we are now in September 8th. You can actually click here. And this is the link where you need to go. So go to this page, and you can download the slides and the code that we will be playing with today. So scroll down, slides, code. But if you have remote access, you don't need to download the code, just proceed here. So let me go to labs and give you a quick orientation. Excuse me, I will go to CD labs. I apologize for pauses in my speech. I'm checking out the questions, and yeah, everybody who did not receive an invitation, you've been noted. And I will fix this at the end of the hour. So inside of labs, we have 2, 3, 4, 5. These correspond to different chapters in our book. And now we will go to chapter number 2. This is the programming models chapter. In this chapter, I have different labs, and for now, I will go to the lab that is native basic. This is what we will be playing with, but to give you an orientation of the system that we are dealing with, let me ignore the, sorry, yeah, I will probably will not distract myself with questions for a few minutes until I'm done explaining this. So this is the contents of the lab. Yeah, every lab has a file like this, instructions.txt, and this file contains step-by-step instructions on the educational exercises that you can do here. Most labs have code. Usually it is the code that is the initial attempt for performance optimization, for example. And also each lab has a folder called solutions. So let me look inside of solutions. There is usually at least one file or several directories inside corresponding to different instruction steps. So you're encouraged to try to follow the steps using the information that you have from the webinars or the slides, or if you have our book, using the book or any other sources. If you give up, you can always go to solutions. And before I start on this lab, let me give you an orientation of what you have in your system. So let's first do that. I'm sorry that I'm doing something wrong. I will do cat proc CPU info, and it shows me the processor information. So disclaimer, the processor that you have in your system is not a real processor. This is a virtualized processor, and in fact it identifies itself as a rather old Intel Xeon, but it is nevertheless a parallel processor. But I'm saying that this is a virtual processor so that you don't rely on performance measurements too seriously. This is just a few cores of Xeon which are also virtualized on top of everything. Now, let me see what I have here. And I will start it with sudo service MPSS status. It says MPSS, the service is running. And now I can run one more command that you will not be able to run if you are in a terminal, but I will run it in the graphical desktop. So this MicSMC is the control panel for Xeon Phi. It shows me that I have one Xeon Phi coprocessor. Well, this is actually the summary for all devices, but I can go here and show my specific device. I can view individual core usage, or I can go and view utilization, temperature. Basically, it shows to me that I have a coprocessor with 57 cores and 8 GB of memory. I can get this information in a different way. If you're in a terminal, you can do that. Sudo mic info. This gives a lot of information in text format, and it shows that I have a Linux host, MPSS version such and such. This is the Xeon Phi. This is the serial number. It actually has the model. This is the model, and so many cores. I have 57 active cores at 1 GHz. Now, this looks like an accelerator, but now let me show to you that this is actually a coprocessor. So I'll go to etc hosts, and it shows to me this very interesting entry. It shows that I have a host called Mike0, and this is the IP address of this host. So let me try to play with this Mike0. I will try to ping it. It pings back. So it's a host that has networking set up. So what about going into it? SSH Mike0. So it allowed me in. As you can see, the prompt has changed. Instead of CDT, I'm now inside of CDT Mike0. And now let's see what's inside. So I have a file system. How big is it? The file system can fit up to 6.4 gigabytes of memory, of data. This file system is living in the RAM disk. But you can see that I'm also mounting a very large directory from the host. So I have access to networking and network file systems. What about my processor? Well, I can do cat proc CPU info. And this went on very quickly, but if I scroll up, there is a lot of lines of input. And actually, what I need to look at is this. This is the ID, 208, 209. It starts with 0, and then it goes all the way down to 227. So I have 228 logical processors. This is 57 cores times 4 hardware threads per core. Okay. So what else can I query here? What about memory? So the memory on my Xeon Phi is 8 gigabytes in size. And actually it's even greater than the host's memory, which is not surprising. This is a virtualized processor. But now let me type exit to go back to the host. So now I'm inside of this directory, and I will try to program my Xeon Phi coprocessor. So to write applications, I will have to use, to edit files, I will have to use a text editor. If you are connected later, when you connect with this remote desktop, you can go to Applications, Accessories, and choose Gedit text editor. This is very convenient for those who are not familiar with Linux text-based editors. It will have code highlighting and everything. Like here, I can navigate to labs, to one basic. This is where we are, hello.cc. So this is easy to work with this file. But if you're working in a terminal, you do not have access to the text-based editors. So let me demonstrate what you can do in the terminal. I will go back here and I will start another session of PuTTY just to be in the same boat as you all. I will open a connection to my host. I'm logged in. So this is what you see now. So what do I have in the way of editing? Well, I can go to labs 201, and then I will have to edit my file hello.cc. Well, if you're familiar with Linux, you can use VI or Emacs. One editor, but they are tricky in that they have really special way of going around the keyboard shortcuts. So you can use Nano. Nano is probably a good compromise for those who are not familiar with Vim or Emacs. So Nano looks like this. It allows you to navigate across the text, and then it has context help. So to save the file, I can do Control-O. To exit, I can do Control-X. I can also do cut-paste. But you will run Nano in one window, and then you can open another window like that to run the applications. So I will actually not use the terminal because I think visually it will be more compelling if I use the remote desktop. and you can use the remote desktop later when you set it up, but this is not very hard. So I will use Emacs to edit this file, and I will keep this terminal open. Okay, so what do we have? We have an application that is exactly that hello world application. It says hello world, I have so many logical cores, and then it makes a Linux system call available in the Linux C standard library. Let me compile this application. I will use the Intel C++ compiler, and I will type hello.cc. This is the file name. When I list, I have a new file called a.out. So a.out is my executable. When I run it, it says hello world, I have 8 logical cores. This is on my host CPU. How do I run this on Xeon Phi? Well, I could try to copy this file to Xeon Phi using SCP. That worked. Let me go to Xeon Phi and run this application. It doesn't run. It says cannot execute binary file because the executable produced for the host is not compatible with Xeon Phi. So now let me try to recompile this file, and one issue that I will find is, well, I don't have the source code on Xeon Phi. Another issue I will find is that I don't have the compiler on Xeon Phi, so I have to exit from Xeon Phi and go back to the host. Okay, I'm back to the host, and I will try to compile my file for Xeon Phi. I will do ACPC, and then I will specify that special flag that cross-compiles for the Xeon Phi architecture -mmic hello.cc. That worked. Now I have a file with the same name. If I try to run it on the host, now it doesn't run. But if I copy it to Xeon Phi, I can run it. And now it reports 228 logical processors. This is 57 cores times 4 hardware threads per core. Alright, so this is my hello world. I'm able to execute a basic application on Xeon Phi. If you look in the instructions, actually it calls for some more experimentation, and let's do that. So one more step that I will do is, well, when I compiled the Xeon Phi executable, it wrote over the Xeon executable. So let me learn to direct output to other files. And I will call it app CPU. This is the output file, the executable file name. So I will compile the CPU application like that, and I will compile the mic application like this. And I will get rid of the a.out file. Okay, so what if I wanted to do some quick tests and I don't have the time to do SCP and SSH? I can run mic native load x, and then I just have to give it the name of the file. So see, I started the application from the host, but it ran on Xeon Phi. This is easy, but what if my application has any dependencies? So I will not include real dependencies in this application, but I will mimic this. I will compile it with an additional argument qopenmp. This will mimic a situation when your application uses OpenMP, the OpenMP library, or which is the parallel framework that we will be using later, or you have your own dependencies. Then, when I do mic native load x, it will complain. It will say, the remote process indicated that the following libraries could not be loaded. lib openmp5.so. And then it says, these are the files that I couldn't find locally, but basically this is the one that's missing. So how do I get this file to Xeon Phi? I have this special location, sync LD library path, that allows MIC native loadx to look for files. But how do I find this file in the first place? Oh, sorry. How do I find this file in the first place? If this is your own library, well, you know where to find it. If this is an Intel library, you can potentially use just locate. And locate printed 3 locations for me. So there are 3 versions of this library. And you can tell from the paths that this is for the 32-bit architecture, for the 64-bit architecture, and one more for the mic architecture. So this is the one I want. So to enable this library on Xeon Phi, I will do export and then sync LD library path. It works much like LD library path, but oh, I'm sorry, this is not what I want to put here. I want to put the path. So I will select everything and then I will do, well, middle mouse button seems to work best. So when I did that, I can go back to MIC native loadx and run the application again. And this time it will find the library and it will transfer it to Xeon Phi temporarily, and it will work. So what if I wanted to run my application on Xeon Phi, but I don't want to use MIC native loadx because I want to work with files. So what do I have on Xeon Phi? Well, I have the stale file. Let me remove a.out. And now let me try to run appmic. It will complain that it cannot find the libraries. So you have to get this library there somehow. Just for the training, we did a configuration tweak that allows you to do it easily. So type mount, and you will see that the installation directory for Intel tools is mounted from the host to the same location on Xeon Phi, which means that I'm on Xeon Phi, but I can do ls opt Intel, and I will find all the files of the Intel Parallel Studio library. Because I already have all these files on Xeon Phi, what I will do is I will set the standard Linux environment variable that allows me to find files, library files, and I will set it to the path where I know this library is located. Opt Intel Composer XE lib mic. And now I can run my application, and it finds the library and it executes. So there we go. We went through setting up a connection with Xeon Phi, and we ran a basic, recompiled and ran a basic application in the native programming model using Xeon Phi basically as a standalone compute node. So there is another lab which uses MPI to run applications. And this is a library for scaling across clusters. We do not really have dedicated sessions in this course for MPI, but I would like to demonstrate what's inside just so that you know what's in MPI and maybe you will want to learn it. So MPI is a framework for scaling using message passing across multiple machines, usually across a cluster. And the very basic hello world application in MPI is like that. You call a special MPI function, MPI init, and then you run whatever code, and then you run MPI finalize. This application will be parallelized. How? You will have process level parallelism. So instead of launching one process like that, you will have at least as many processes as you have compute nodes. I can treat a Xeon Phi as a compute node, so in principle, I can run one process on the host and one process on Xeon Phi, and they will both use the same code. This function MPI init allows me to propagate the input arguments to all processes, and also it allows them to find each other. Then I can use additional MPI calls to identify the role of each process, to pass any data around that I need to pass. But basically, I will have a parallel process. So let's learn how to program with MPI, how to run applications using MPI on Xeon Phi coprocessors. So first, let me run an MPI application on the host. I will use the tool MPI ICPC. This is a wrapper for MPI around the Intel C++ compiler, and I will produce an executable called hello from this source file, hello mpi.cc. This executable can just be run, no issues, but I can also run it in parallel using an instruction like that. MPI run cdt. This is my host name. Oh, I'm sorry, MPI run host cdt. NP, this is the number of processes that I want to put on this compute node. And let me specify 8, well, I have 8 logical cores, so I will run one process on each core. For Xeon Phi, by the way, this is not an optimal strategy, but I can at least do that. And then I have to specify the full path to this executable. Actually, just this will be enough. Well, relative path will be enough. And here we go. This process was run in 8 instances. So I can potentially do the same with Xeon Phi. So to compile for Xeon Phi, I will have to do MPI ICPC. This is compilation. I will produce a different executable. I will call it hello.mic, hello.xeonphi, and I will use an additional argument, -mmic. So as you can see, I produced a second executable, and when I run it, it doesn't run, because this is an executable for the Xeon Phi architecture. So let me go back to that command that I used, and let me change the host to mic0. Well, when I do this, many problems will happen, so I will illustrate all these problems, and you will learn how to identify and resolve them. One problem is this: PMI proxy cannot execute binary file. That is because the Intel MPI library is not ready to run on Xeon Phi. So before I can do that, I have to set this variable I MPI mic equals 1. It tells the Intel MPI library that I'm going to use Xeon Phi coprocessors. So now I run again, and I get a different error. It says exec vp error on file.hello, no such directory. Well, duh, as they say around here. I specified the wrong executable. How about I specify the correct executable? Still the same error. What's happening? Well, this executable has to exist on the host on which I'm running. Does it? I go to mic0, do ls. No, there is no such executable. So I need to put it there. Now, when I go to mic0, I find the executable there. Okay, so now it's got to run. And I tried to run it again. Still no luck. Well, let me check everything. I actually have this relative path, so I need to change it to the actual path. The actual path is in my home directory. Okay, so finally it ran on Xeon Phi with multiple processes. Well, the purpose of MPI is not so much to parallelize across multiple cores inside the system, but to parallelize across multiple independent compute nodes. And you can do it like that. You can specify one host like this and another host like that. Colon host cdt, number of processes, well, let's make it different, 4. And then the executable will be hello period. As you can see, I've just run an application that uses some cores on the Xeon and some cores on the Xeon Phi. And MPI allows me to communicate data between this process and this other process. And MPI can scale across hundreds and thousands of processes. Of course, I don't want to specify them all in the command line. Instead, I will do something like this. I will edit a file. I will create a new file, and I will call it hosts.txt. And in this file, I will put one host, which is CDT, and it will use 4 processes. And I will put another host, CDT mic 0, and it will use 8 processes. So I have, oops, sorry. Now I have, oh, I'm sorry. Let me try it again. How about like this? Oh, try again. CDT, yeah, like this. So now I have hosts.txt, which has line by line all the hosts on which I want to run. And in principle, I can just do MPI run hosts.txt. I think the syntax is machine file hosts.txt, and then the executable file name. This is not going to run because I have a lot of problems. One is that MPI thinks that this is the name of the executable for both platforms, and the other problem is that it's looking for this executable in my home directory. So to put the host executable in the home directory, I will copy hello to the home directory on the host. And then this at least is slightly better. Now it can find the host executable, but not the Xeon Phi executable. And to tell MPI that the difference between host executables and Xeon Phi executables is this suffix .xeon Phi, I will set another variable, MPI mic postfix, and I will set it to this postfix. Now MPI will know that if hello is the name of the executable, then this is the name of the executable for the CPU. But for Xeon Phi, it has to look for hello.Xeon Phi. And now I can run my application and it scales. So this is the basic approach of programming Xeon Phi coprocessors with the native model. I use the same exact code as on the host, and if networking configuration and file system configuration allows, then I can just run my application on Xeon Phi using MPI or as a standalone process without any code modification. As for another approach of load programming, where you have to insert certain statements in the code, we will discuss it tomorrow. And before I say goodbye, I want to make a couple of, first of all, let me check with the questions if any questions came in that can be addressed globally. Yes, so one question is, can we use TBB and Silk Plus on Xeon Phi? I apologize for the delay with this question, came in about an hour ago. TBB is threading building blocks. Silk Plus is a different, I'm sorry, TBB is threading building blocks. This is a parallel framework. Silk Plus is also a parallel framework. And I mentioned OpenMP today. This is a third parallel framework. They all are supported on Xeon and on Xeon Phi, and you can absolutely use them. TBB supplied with the Intel compilers has an implementation for the Xeon Phi architecture. We will talk about parallelism starting this Friday. As for MPI, this is a different framework. So the frameworks that I named, TBB, Silk Plus, and OpenMP, they are all frameworks for multi-threading. Which means that with TBB you can run your application on multiple cores within one system. With Silk Plus you can run your application on multiple cores within one system or one Xeon Phi. With OpenMP you can run application with multiple cores on one compute node. MPI is also a parallel framework, but MPI is a framework for distributed computing. So MPI allows me to run multiple processes on multiple compute nodes. I can use MPI instead of the threading frameworks, but we will see that this is often disadvantageous because there is too much communication and possibly too much memory overhead when doing that. So usually you have to combine MPI with one of the frameworks such as OpenMP, Silk Plus, and threading building blocks, and we will talk about this on Friday. Another question that came in is, does strace work on Xeon Phi? And I don't know, but it's really easy to check. We will go and actually I will demonstrate something else that's pretty cool. So I logged into Xeon Phi, strace. Yeah, not found. So possibly you can recompile it, but not out of the box. But something cool I wanted to show on Xeon Phi is that this is a real Linux operating system. So it has a Linux kernel, and it also has a lot of Linux tools. One of the tools that I really like having on Xeon Phi is a text editor, VI. And I can use it to open, for example, one of the configuration files. So I can edit files on Xeon Phi, and I will not try to mess with my configuration, but at least I have this opportunity. I will address whatever questions are left offline because we are out of time. See you tomorrow the same time. If you have mentioned to me that you did not receive remote access, I will contact you. If you have technical issues, write to training@colfaxinternational.com, and we will reassemble tomorrow, same time, and talk about offload model of Xeon Phi programming. Thank you very much. Bye-bye.